For those who are new, this series uses www.falstad.com for circuit simulations. Hello again, everyone. Welcome to the Falstad Resistors simulation. But why do we even need resistors? The combination of resistors in a circuit determines how much current flows through it. And based on that, the voltage across each resistor also changes. A resistor limits current by opposing the flow of electrons. When voltage pushes current through a circuit, the resistor creates resistance, like friction for electricity. The higher the resistance, the harder it is for current to pass, so less current flows. This relationship is described by Ohm's law. If you don't know Ohm's law or have forgotten it, you can watch the Ohm's law video because you will need it quite a lot. It's essential for calculating currents, voltages, and understanding how resistors affect a circuit. So, increasing resistance decreases current. To determine the amount of current flowing through the circuit and the voltage across each resistor, we first simplify the circuit. Only the closed switches allow current to pass, completing the circuit and enabling electricity to flow. In simple terms, these laws help us calculate currents and voltages in complex circuits. While analyzing the circuit, we will frequently call Kirchhoff's laws to determine currents and voltages accurately. These laws serve as guidelines to ensure that current and voltage are correctly accounted for in every part of the circuit. First, we calculate the total resistance of the parallel resistors. If we label the resistors as R1, R2, and R3, with R1 and R2 in parallel, the total resistance of R1 and R2 is R12 equals R1 times R2 divided by R1 plus R2. That is 100 ohms times 800 ohms divided by 100 plus 800, which equals 88.88 ohms. Next, we add the series resistor R3 to find the total resistance R123 equals R12 plus R3, that is 88.88 plus 200, which equals 288.88 ohms. Now, calculate the total current. I equals V divided by R123. That is 5 volts divided by 288.88 ohms, which is approximately 17.3 mA. Since we've calculated the total current, now we can work backward to return the circuit to its original configuration and calculate the voltage and current across each resistor. Here's how we do it step by step. Time to recall Kirchhoff's laws. In a series connection, the current is the same through all components in that branch. So, the current through R3 is equal to the total current. I3 equals 17.308 mA. Voltage across R12. V12 equals I times R12, which is 0.017308 amps times 88.88 ohms, approximately 1.538 volts. Voltage across R3. V3 equals I3 times R3, which is 0.017308 amps times 200 ohms, approximately 3.462 volts. Voltage across the parallel resistors R1 and R2. The voltage across resistors in parallel is the same for both. Current through each parallel resistor. I1 equals V underscore R1 divided by R1. 1.538 volts divided by 100 ohms, approximately 15.38 mA. I2 equals V underscore R2 divided by R2. 1.538 volts divided by 800 ohms, approximately 1.923 mA. Check. The sum of the currents through R1 and R2 equals the total current entering the parallel branch. I1 plus I2 is approximately 17.308 mA. Perfect. Now, you can challenge yourself by trying other combinations in the circuit. If we consider that the circuit has 6 switches, calculating all 30 different combinations will be quite interesting. To check your results, you can use the window in the bottom right corner. If you enjoyed the video, don't forget to like it, share the link, and subscribe for support. See you in the next video. Bye.